What you're looking at is your home, Earth. No doubt you'll agree with me when I say that this is a great place. We've got water here, fire, and complex life forms, such as you. On this planet, there is much movement. We've got walking people, racing cars, grazing elephants, flying footballs and planes, speedy bikes, hovering birds. Even the Earth itself is moving. It's continually rotating and revolving around a gigantic ball of fire. All this motion is one good reason as to why Earth is an interesting and lively place to do physics. Predicting motion and modeling the positions of moving bodies traveling through space is a big part of physics. Let's plunge right into the physics of motion, starting first with basic terminology. Scalars, vectors, position, time, distance, displacement, speed, velocity, acceleration, deceleration, intimidation through excessive intake of seemingly never-ending jargon. These are all words you may have heard of as they are thrown around a lot in everyday life. A scalar is a quantity that conveys magnitude. A vector is a quantity that conveys both magnitude and a direction. Mass is an example of a scalar quantity. It is colloquially termed as the amount of stuff in an object, and it's measured in kilograms. You say, I have a mass of 75 kilograms. There is no direction specified here. On the other hand, force is an example of a vector quantity. If I had two footballs in front of me and I were to kick the first one ahead in the forward direction very hard and kick the second one in the backward direction softly, there's a big difference. In both scenarios, it is clear that the direction associated with the two forces was completely opposite. One was kicked ahead and the other was kicked backward, and the first kick has a much greater magnitude than the second kick. We'll return to mass and forces in a moment. I would like for you to meet Jonathan Shetty, an amateur cyclist, biking down the road from west to east with great speed. The term position describes his exact place in the universe. His position right now is here. 5 seconds ago it was there, and in 3 seconds it will be here. Under position, there is displacement and distance. Time is basically how long he's been riding for. In this case, it's 10 seconds. If you noticed, with time, his position was changing. When time equals 0, or when he had been riding for 0 seconds, which was just when he got onto the bike, his position was here. Then, 1 second into the ride, when t equals 1, his position was here. As time changed, so did his position. After 10 seconds, his position was here. And that was the end of his journey. His position changed with time, and as you can see, with every passing second, he had covered more ground. He had covered more distance. The overall distance covered is 30 meters. The distance between his final position, when his journey ended after 10 seconds, and his initial position, when his journey had just begun, is called the displacement. The displacement is the change in position of an object, in this case 30 meters. If Jonathan were to cycle back to his initial position in the same way, his displacement would be minus 30 meters. Why? Isn't he traveling the same distance? Well, good question. Remember scalars and vectors? Time and distance are scalars, whereas displacement is a vector. We usually discuss displacement in a coordinate axis. Let's say I draw a Cartesian plane here. The origin or 0, 0 point on this axis is the starting point. The eastward and westward directions are the positive and negative directions in the x dimension. There is also the y dimension, where north is positive and south is negative. But since Jonathan is only moving through the x dimension, we can ignore y. We can calculate the displacement of a moving object using this formula. Displacement equals final position minus initial position, or delta x equals xf minus xi. This is the very first equation of this series. So, Jonathan moved 30 meters eastward. He traveled in the positive direction by 30 meters, and so his distance and displacement was plus 30. His coordinates went from 0, 0 to 30, 0. If he were to travel back, he would move in the negative x direction, back to 0, 0, and so his displacement would be negative 30, but the distance traveled would still be 30 meters. The direction of travel can affect the displacement, but not the distance. By the way, it isn't compulsory that east has to be positive and west be negative. It could be the opposite. The signs associated with each direction are decided by you. That's the cool thing about physics. You can model things to your liking. Now, let us say that from 0, 0, Jonathan cycles 10 meters in the westward direction. That means he travels minus 10 meters in the x dimension. He gets to the point minus 10, 0 and greets his friend Sunita. His displacement was negative 10 meters, while his distance covered was 10 meters. Those 10 meters took 10 seconds to cover. So how fast was Jonathan moving? What was his speed? What is speed? Speed is basically the rate at which a moving body is covering distance. If I were standing at point 0 and I moved to point 1, then point 2, then stopped at point 3. If it took me 3 seconds to move through those 3 points, asking how fast I was moving is equivalent to asking how much distance I covered per unit time, or how many points I covered per second. Speed is the rate of change of position. Speed is the distance moved per unit time. Since the units of time is seconds, speed is the distance moved per second. Speed is equal to distance divided by time. Jonathan Shetty covered a distance of 10 meters in 10 seconds. Plug in those values into this equation and you'll get that he traveled at a speed of 1 meter per second. However, his velocity was minus 1 meters per second. What is velocity? Well, velocity is the change in position divided by the change in time. The rate of change of position is velocity. How is that different from speed? Remember scalars and vectors? Speed is a scalar quantity, whereas velocity is a vector quantity. Speed is the rate of change of distance with time, whereas velocity is the rate of change of displacement with time. Remember, distance is a scalar. It is always positive and is only concerned with how many meters you traveled. Conversely, displacement is a vector and talks about direction of final position with respect to the initial position. The direction of velocity can be represented through the sign, positive or negative, of the velocity value by drawing a velocity vector on, for example, a grid and noting it down in normal English. In this case, Jonathan's velocity was minus 1 meters per second, or 1 meter per second westward. Here are the mathematical formulae for speed and velocity. Speed is distance over time. Velocity is displacement over time. Both distance and displacement are related to position, hence why velocity is often confused with speed. This motion that we are looking at is an example of one-dimensional motion. Jonathan is moving in the x dimension, which is to say he is moving only eastward and westward, right and left. He is not moving in the y dimension, up and down, and most definitely not moving in 3 dimensions. Jonathan's velocity is 1 meter per second westward. That means that for every single moment of the journey, he was traveling at the same pace, minus 1 meters per second. If we were to draw a graph with time on the x-axis and velocity on the y-axis, we would get a horizontal line because velocity is minus 1 meters per second regardless of the value of time. According to this graph, it took Jonathan 0 seconds to start pedaling to reach the speed of 1 meter per second and 0 seconds to brake and stop at a standstill to avoid ramming into Sunita. Think, does that make sense to you? To me it does not, and indeed it is impossible for Jonathan to do this. What really happened was that he spent the opening few seconds getting a move on and pedaling. Then for the middle portion he kept pedaling to maintain his speed, and for the final few seconds decreased his speed until he completely stopped, ensuring that Sunita would be safe. At each moment his velocity was different. So, why did our minus 1 meter per second value fail us? Why did it not correspond with what was really happening? Well, you see, this value is the average value for velocity. It is not the instantaneous value for velocity. So let's emphasize that into our equation. Average velocity is equal to total displacement divided by time taken. V equals delta S by delta T. If you were paying attention, you'll know that at the beginning of the video, I said, even the Earth itself is moving. It's continually rotating and revolving around a gigantic ball of fire. This is indeed true. The Earth is rotating at the equator at a speed of around 470 meters per second. The Earth is revolving around the Sun at 30,000 meters per second. The Sun is revolving around a supermassive black hole in the center of our galaxy at the speed of 220,000 meters per second, and our galaxy, the Milky Way, is moving through the vastness of our universe at 230,000 meters per second. On the basis of this, you might say that Jonathan Shetty cannot be traveling with a velocity of minus 1 meters per second, because clearly his velocity should be 230,000 meters per second plus 220,000 meters per second. But no, I'm here to tell you that we do not do that here. When we say that Jonathan is biking at minus 1 meters per second, we are ignoring the motion of the planet that he's on, the Sun and the Milky Way. When I say that Jonathan Shetty is moving at a velocity of minus 1 meters per second, I am pretending that the Earth's surface is not moving, that it's completely still, even though it really isn't. Relative to the surface of this quote-unquote completely still Earth, Jonathan Shetty's velocity is indeed minus 1 meters per second. In this case, the Earth is my inertial reference frame. The inertial reference frame is the object or surface that we pretend is completely still. If I was driving a car on the surface of the moon at a speed of 5 meters per second, I would ignore the motion of the moon revolving around the Earth and pretend that it's unmoving. The moon would be my inertial reference frame. My speed then, relative to the surface of the moon, would be 5 meters per second. In the early momentary burst of speed and the late lapse of speed, Jonathan's velocity was not uniform. Early into the race, his velocity was increasing from 0 to his highest achieved speed, and toward the end, he was slowing back down to 0. In both situations, he was accelerating. Acceleration is the change in velocity of an object over time, and it too is a vector. It is measured in meters per second, or meters per second squared. Say you are cruising down the city highway on an empty Sunday. You are on cruise control and your velocity is a steady 100 kilometers per hour. In this situation, your acceleration is equal to 0. This is because acceleration is the change in velocity of an object, and your velocity is unchanging on the serene highway. However, if you were driving through the main streets of the city on the Monday after during rush hour, your velocity would constantly be changing as you would be maneuvering through traffic and different intersections and stopping at traffic lights and taking off from there. So, at different points in your journey, you'll be accelerating in different ways.
What do you mean different ways? Oh, come on, remember scalars and vectors?
Acceleration is a vector, which means that just like velocity, it can be both positive and negative. In your Monday rush hour routine, you might come across a situation like this. You are at a stoplight. You see it turn green and boom, you floor it. You accelerate from 0 kilometers per hour to 100 kilometers per hour in 10 seconds. And from there, you maintain your velocity at 100 for some distance. Then you see a line of cars ahead. You slam the brakes and go from 100 to 0 yet again. Boom, you're back at another stoplight. In this situation, your velocity went from 0 to 100 in the beginning and back to 0 in the end. In these moments, you were accelerating, as there was a change in your velocity. In the middle portion of the journey, you were cruising at 100, so your acceleration was 0, since your velocity was constant. When you floored the gas, your velocity was increasing, whereas when you slammed the brakes, your velocity was decreasing. In both instances, you were accelerating in different ways. In the beginning, your acceleration was positive, and in the end, it was negative. Therefore, in the beginning, the direction of the acceleration was the same as the velocity, which is why you moved faster. And conversely, in the end, your acceleration was in the opposite direction of your velocity, which is why you moved slower and slower. When your velocity decreases, by the way, we often say that you are decelerating.
Alright, we've crossed the basics. Hopefully none of this jargon intimidates you now.
To study the motion of moving bodies, we have to take all of these variables associated with motion and formulate an equation containing them. Well, unsurprisingly, since there are so many variables and so much varying motion to behold on our planet, we actually have a whole set of equations. They are called the kinematic equations. Kinematics is the study of the motion of objects, omitting the forces acting upon them.
Hi, thank you for watching this video. If you feel certain explanations weren't understandable or you have any questions related to them, please write to me in the comments section or through Gmail. If you'd like to know which resources have been used to research and create this video, I've linked a document containing them underneath. I've also linked a short worksheet that you can solve to test your understanding of this topic. Goodbye.